An important subset of the ordered solids are covalent network solids, and that'll be the subject of this video. Our learning goals for this will be the structure of covalent network solids, and we'll contrast that a little bit with the structure of metallic and ionic compounds, and also the variety of silicon oxide solids that can occur. So what are covalent networks? Essentially, they're non-metallic substances, either elements or oxides, that form an infinite array of covalent bonds. They're held together by covalent bonds. We've seen earlier examples of this in the carbon allotropes. For example, diamond is a covalent network solid, as is graphite. Among the properties one finds in these solids are that their electrons typically are located in bonds. They're localized in bonds, so they don't freely flow from one part of the solid to another, which means that many of them are not very good conductors, although some of them do serve as semiconductors. Graphite, on the other hand, is a good conductor simply because it has an extended pi system that allows electrons to flow freely across its surface. DSR EPR local geometries are the ones that are found among these covalent bonds. So these substances tend not to be malleable or ductile. They like to retain their shape. And in fact, in many cases, if you try to change that shape, you could actually break them or shatter them. They can be either hard or soft. So these are some of the things that distinguish these covalent network solids from the ones that we've seen. Now, carbon and silicon are both in the group of elements that form these covalent network solids, but their oxides contrast one another. So let's take a look at that in a little bit more detail. Carbon and silicon lie above one another in the periodic table, which means that they have similar chemistry and similar properties. They both have a bonding capacity of 4. We know that carbon is more electronegative than silicon. They have similar compounds and similar chemistry. They make similar hydrides and halides. So what does this mean about their oxides? Well, it turns out we know about the oxide of carbon. It's a gas, it's carbon dioxide. It's a component of the atmosphere. It has no dipole moment, though it does have polar bonds. Silicon also forms a dioxide, but in this case it's a hard crystalline solid. It also is made up of polar covalent bonds, but it has a very high melting point, so you're not likely to see silicon dioxide gas anytime in your lifetime. Now, silicon dioxide has a more common name. We know it as quartz. In quartz, each oxygen makes 2 bonds and each silicon makes 4, so we need twice as many oxygens as we have silicons. That's why it has an empirical formula of SiO2. The result in SiO2, though, is an extended network of these silicon-oxygen covalent bonds. Now, we can grasp this a little better if we look at a model for it. So here's a silicon atom. Each silicon is going to be bonded to 4 oxygen atoms. It has a tetrahedral arrangement as predicted by VSEPR model. Each of these silicon units, though, is going to be connected to other silicon units. And you'll notice that in each of these cases, we have between any 2 silicon atoms, we have an oxygen atom. So this forms an extended network that basically makes an ordered solid. This is quartz. And here we can see a picture of quartz, and we can see that indeed it is an ordered solid. Again, the red atoms are the oxygen atoms, so that we see between any pair of silicon atoms, we have a pair of oxygen atoms, forming this extended network. Should also note that silicon dioxide is the fundamental ingredient of both sand and glass. Let's contrast this now with carbon dioxide, which clearly is not an extended solid. One can imagine what it would take to make carbon into an extended solid, and the problem with it is that energetically carbon would rather form these double bonds to oxygen, which means that I can only create a closed compound of 3 atoms with all of the valences satisfied, and this is an energetically favorable solution for carbon dioxide. However, the silicon-oxygen double bond is not nearly as energetically favorable, so silicon actually finds for silicon, the energetically favorable solution is to form this extended solid network and to have oxygens bridging pairs of silicon atoms. So in a sense, there's a small subtle difference between carbon and silicon here, but it makes all the difference when it comes to what sort of oxide these 2 elements form. One thing you may not know about quartz is that it is a chiral substance. However, in biology, we find that most substances come in a single enantiomer, but in the case of quartz, actually both enantiomers are observed naturally. If we look at quartz and we look at its mirror image, you can certainly tell that this is a mirror image, but it may be more difficult to pick out the subtle features that make these two mirror images not superimposable on one another. And in fact, I can't point them out to you in this sort of picture. Nevertheless, they are distinct enantiomers, and as I said, they both exist in nature. Now, one of the things that one can do with silicon dioxide, and particularly when it is in sand, is we can grind it up, melt it down, and use it to form particular shapes that we want. Okay, this is the process of making glass. So glass is produced by melting sand and then cooling it slowly in sometimes in preformed molds so that we're creating it in a particular shape. While it's being cooled is when we generally give it the shape that we want it to have. It is a less crystalline form of silicon dioxide than quartz. In fact, it is a disordered solid or a semi-ordered solid. But there was a time when it was believed that glass might be a slow-flowing liquid. Now, why would they think that? In medieval times, stained glass windows in churches were made, and many of those stained glass windows still exist today. And people who have studied those have noted that the bottoms of the windows tend to be thicker than the tops. Now, it turns out that while this was believed to be indication that the glass was slowly flowing downward due to gravitational force, it has been established since then that in fact this is not the case, that in fact this is an artifact of the manufacturing process, and in fact it provided a little bit more stability for these windows to have the bottoms be a little bit thicker. Today we can enjoy glass in a variety of forms, not only in our windows but also in various artistic forms like the one shown here. I hope this has given you some insight into not only covalent solids, but a little bit of insight into silicon dioxide as a covalent network solid.